Okay, so in the last video, we finished up with liquids, so we're going to go ahead and move on to gases. So we've gone over solids so far, which are super strong bonds. Everything stays the shape it is and the size it is. Liquids are weaker bonds. Liquids can flow, so it allows them to take the shape of their container, but they're not going to rapidly increase in size. Then we have gases. So gases sort of do things a little bit differently. Gases are moving super fast. So inside of a container, a gas is kind of moving like this. If you look around you, there's gases all around you. You just can't see it. And they are moving kind of like my pointer is on this screen. They're constantly bouncing off of everything and just going like crazy. And they never stop. That's what allows you to walk into somewhere like a Bon-Ton and instantly smell the perfume counter. It's because they're gases, and those gases are spreading out super, super fast. So the molecules of a gas, let's say we're looking here at this bromine gas, they're constantly moving around inside of this flask, and they're moving faster than a liquid. So as soon as I take the top off of this container, the gas is going to suddenly explode out everywhere because the particles are moving so fast. That's why if you take a bottle of, let's say, Windex and open it up, you smell that Windex right away. That's the gases escaping the container. And gases will take the shape of their container. So when I put a gas into this container, it's going to fill it up all the way because those gases are constantly moving around. And as soon as they have more space to spread out, like I take the top off of this container, they're going to spread out as much as they possibly can. So gases will try to take up as much volume as possible and spread themselves out, totally unlike liquids and solids. So when we look at what all this stuff is, okay, so we're kind of looking at everything together here, and you have this picture on your screen or on your paper, but solids, liquids, and gases can turn into each other very easily, and it's through these processes. So if I want to turn a solid into a liquid, I melt it. If I want to turn a liquid into a gas, I vaporize it. But if I want to turn a gas back into a liquid, it's what we call condensation, and then a liquid can turn into a solid by freezing. So if I have molten iron that I want to turn into, I don't know, a sword or something cool like that, I would take that liquid iron and I would cool it by what's called freezing to turn it back into a solid. So that might not necessarily mean I stick it in a freezer, but that just means I'm allowing it to cool to the point of turning back into a solid. Now, some weird things can happen sometimes when we're looking at these state changes, we call them. Once in a while, I can have a solid turn directly into a gas. It skips liquid altogether, and it's suddenly what we call sublime. So that's kind of where the band name comes from. But sublime or sublimation is where a solid turns directly into a gas. This happens if you've ever seen dry ice before. As soon as you open up the container, a dry ice is a very unstable solid. It wants to turn into a liquid or a gas as soon as possible. So as soon as you open up that container and it heats up, it doesn't even get a chance to turn into a liquid because it suddenly sublimes and turns itself into a gas, which is why you always see dry ice kind of smoking. The same thing happens going in the other way, turning a gas into a liquid, into a solid, and that is called deposition. So once in a while, if it's cold enough, you can actually take a pot of boiling water. So boiling water is going from that liquid to the gaseous state, that vaporization, and those gaseous water molecules, if they get cold rapidly enough, if you take a pot of boiling water and chuck it out in maybe negative 10 degrees Fahrenheit, that actual gas particles will condense themselves and actually turn into solid ice droplets, and it'll look like it's snowing. So it's kind of cool, a little dangerous. I would try it, but it is an example of deposition. So when we look at matter, okay, matter is all of this stuff kind of we separate. So matter is all the things in the universe, and we separate it down into two major categories, either pure substances or mixtures. And we're going to look at the pure substances first. So pure substances is where all the particles that are inside a sample are the same. So it could be all copper molecule or copper atoms here. So if you're looking at a piece of copper wire, that's a pure substance because it's made of 100% copper. If I'm looking at, let's say, distilled water, the kind that you buy in the jugs at the store, distilled water is pure water. It's all it's made of. And water is made of one oxygen, two hydrogens. That's why it's H2O. So pure substances can be elements where it's all the same type of atom, either copper, it could be nickel, it could be anything on the periodic table. Pure substances, if it's just made of that, that's pure substance, and those are what are called elements. And then compounds are where we have all the same type of molecules when we take atoms and stick them together. So water is a molecule because it's made of multiple types of atoms. So pure substances can be elements and compounds, but the key here is that the particles are all the same. But what if we have different types of particles? Let's say we have something like this, where there's all different types of particles that are present. That's what we call a mixture. So a mixture is going to be where we have either elements or compounds all mixed together and they're not chemically combined. So that's the big key here. A mixture is not chemically combined. If I look at the salad I had for lunch, okay, I can separate that out because my tomato hasn't chemically combined to my lettuce. The same thing goes when we look at things in chemistry. Mixtures are things where we have two or more substances in the same container, but they're not chemically combined. I can pick them apart through different separation techniques. When we did our lab this week, where you looked at separating out the iron from the sand and the salt, that was a mixture. They weren't chemically combined. Otherwise, you wouldn't have been able to separate it using filtration and using evaporation and using the magnet, okay? None of those things would have worked. So when we look at mixtures, mixtures can be things like tap water, where we have things dissolved in it. I can get those things dissolved out by evaporating. It could be something like steel, where it's a mixture of two metals that are mixed together in the same container, but they're not chemically combined. That's what we call an alloy. Or it could even be something like the air you're breathing. That's a huge mixture of all different types of gases that we just breathe in as one thing, but there's all different types of materials that are in there that are not chemically combined. So when we look at our types of mixtures, we have homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures, with the root word, means the same throughout. So a homogeneous mixture is going to look totally the same. It's not going to look different based on where you're looking in the container. So if I look at this glass of tea here, I can't really see any differences in this container between maybe the top and the bottom. It looks all the same because it's homogeneous. The air you're breathing is homogeneous. You take in a breath right now, you breathe. You've breathed in the same amount of all of these materials that you will in your next breath because it's the same throughout. It's thoroughly mixed, okay? We also will call these what are known as a solution. So if you drink black coffee, that's a solution. If you drink Kool-Aid, that's a solution. The Gatorade you drink is a solution. Gatorade is not a whole bunch of electrolytes chemically bonded to the water. They're just mixed together. The reason you can't see this is because the particles are so small. That's what makes it a solution. But we look at heterogeneous mixtures. These things look totally different. So something like this mix right here, oh my gosh, this looks so different. I can pick that apart so easily. Or something like oil and water looks very, very different. I can see obvious differences. Even something like blood, where we have kind of even smaller differences. Blood is what is known as clicked on my picture. Blood is heterogeneous because it has red blood cells, it has lymphocytes, it has all kinds of different stuff mixed in there. So heterogeneous are not uniform. They can be separated from one another, and we can call these suspensions or colloids. So whether or not you have a suspension or a colloid or a solution, it just depends on how big the particles are. Tiny particles are solutions, colloids are medium-sized particles, and suspensions are big, heavy particles. Okay, so colloids will see medium particles, and they'll scatter light. So I can shine a flashlight through a colloid, maybe something like fog, and I'll see that beam of light. But trying to do that through a solution doesn't work. And you want to make sure that you see me so you can actually see an example of this. And we're going to have a lab on this as well. And then suspensions have these big, heavy particles. These are what are going to settle out over time. So if you have, let's say, salad dressing, something like Italian salad dressing, you shake it up so you can get all the bits poured on your salad, but they're going to settle out over time. They're not going to stay separated very long, or they're going to separate almost immediately because they are a suspension, okay? So that's why it'll say certain things like shake before use. It's because they're suspensions and you've got big, heavy particles. So this kind of stuff applies to even things that we use in our daily life. So if you have any questions on how matter is classified, these are just our notes for this. We're going to be practicing this a ton, so do not stress if this is like a lot at once. We're going to go over all this, but I just wanted to make sure that you have all the notes ready to go so you can use them. And that is it. If I can get this stopped. Okay, thank you.